Welcome back to the Dev Sandbox. Today, we're doing a bit of a creative workshop to completely dismantle this stubborn myth of the unhackable AI. We're booting things up to run through some real, cutting-edge red team experiments straight out of the May 2026 vulnerability report. Throughout this explainer, we're going behind the curtain, deep into the code, to see exactly how the most advanced, supposedly secure frontier models are being systematically compromised right now. Let's get right into it. Okay, 95%. Just let that number sink in for a second. That is the staggering attack success rate we're currently seeing against heavily aligned frontier AI systems. And no, they aren't pulling this off with those old-school, simple keyword tricks you might be used to. Attackers are hitting this massive success rate by leveraging advanced state space manipulation. We have moved way past the traditional boundaries of AI security. What we're witnessing here is a massive industry shift. For the longest time, prompt engineering was the absolute gold standard. We kind of thought of AI interaction as this puzzle where you just had to find that one perfect static sentence to get your output. But turns out those static inputs are incredibly fragile. We literally have to toss out that old playbook because, honestly, prompt engineering is dead. Today, we're acting as context designers. We're dynamically orchestrating entire data environments to feed the AI the exact parameters it needs to understand its operational boundaries. And, as we'll see, when you manipulate that context, you completely manipulate the AI's behavior. All right, let's dive right into our first terminal. Experiment 1, the memory hack. So to target systems that use persistent episodic memory, we're talking models like Kimi K2.5, we actually rely on degrading what's called contextual integrity. You can think of contextual integrity as the AI's internal compass for information flow compliance. The fundamental flaw in AI security right now is this naive assumption that a model can always tell the difference between trusted system instructions and untrusted user data. By degrading this contextual integrity, researchers have mathematically proven that an adversary can always, without fail, construct a context where a highly harmful flow looks perfectly legitimate to the AI's internal sensors. When we run this side by side, you'll notice we aren't using complex hacker jargon at all. Instead, we're taking highly malicious unrestricted coding instructions, specifically the ENI Smol variant, and we're wrapping them up inside the incredibly boring, mundane camouflage of a corporate master service agreement. We feed this MSA addendum to the AI, and because the system inherently trusts that authoritative legal domain formatting, it obediently summarizes those malicious rules and permanently poisons its own episodic memory. It completely bypasses standard filters because, well, it just thinks it's filing paperwork. And what's truly shocking about this is just how effective that disguise actually is. It absolutely tanks the upstream detection rate down to a mere 9.7% on cutting-edge architectures like Llama 3.1. The AI's security agents are basically being fooled by a digital suit and tie, totally failing to scrutinize the actual semantic threat hiding just underneath. Moving right along to our second terminal, Experiment 2, the time bomb. Now, to target multi-agent systems, we use this highly evasive time delay tactic known as temporal scattering. Essentially, this means we're taking a single, highly dangerous objective and breaking it down into tiny, totally innocent-looking fragments. Then we just sprinkle those fragments across multiple, separate conversational turns. By doing this, we completely bypass isolated safety filters, because those filters, they only have the memory to evaluate one single message at a time. They can't see the big picture. Let's actually compile this 4-turn conversational attack together in the sandbox. Step 1 is totally innocent networking theory. We're just asking for a standard TCP/SYN explanation. Nothing crazy. But by step 2, we inject a directional stimulus, asking about raw socket flags for diagnostics. Still seems okay, right? Then step 3, we request a basic Python script for this diagnostic mapping. And suddenly, boom, by step 4, we append timing parameters to ensure our packets aren't dropped. We are completely bypassing their security by slowly boiling the frog. So if you analyze them individually, these are just 4 separate, totally harmless-looking educational questions. No single step is going to trigger an alarm. But the agent's core orchestration module, which is literally designed to be helpful and constantly build upon preceding context, inevitably algorithmically stitches those scattered puzzle pieces together into one fully functional, highly stealthy network evasion payload. Deploying these semantic and temporal scattering evasions elevates the average risk trigger rate to over 52% across 10 leading autonomous models. That is a massive jump. It absolutely proves that the AI assistants we are trusting to automate our workflows are completely unequipped to handle threats that are dispersed over time. It's a glaring blind spot for the whole industry. All right, let's step over to our final terminal for today, Experiment 3, the weight shifter. For this one, we're exploiting real-time architectural adaptations, specifically targeting a mechanism called test-time training, or TTT. Now, TTT is an amazing cutting-edge feature. It allows models to dynamically adapt their internal parameters, literally changing their weights during the inference phase right before they answer a query, all to boost complex reasoning. It's brilliant, but it inadvertently creates this massive vulnerability that can entirely override all the static safety guardrails that were hard-coded during pre-training. Tracking our fine-tuning parameters across different threat phases, a pretty terrifying pattern starts to emerge. If we force the model to make continuous updates during the generation or few-shot phases, we hit an absolutely devastating 93 to 95% attack success rate using LoRa configurations. We are quite literally using the model's own dynamic reasoning engine against it, forcing it to recalibrate its safety parameters on the fly. See what happens when we demand a deep, continuous linguistic analysis of persuasive phishing typologies. We're essentially forcing the model to think repetitively about psychological manipulation. And as it processes this, its localized weights physically alter. It's basically brainwashing itself, shifting away from its safety alignment in real time. By the time it finishes processing, it happily spits out a highly detailed, fully operational IT admin phishing template. So, the absolutely crucial point we've discovered in the lab today is chilling, but simple. Static safety is dead. All those heuristic filters, the basic RLHF, the attempts to neatly separate data from instructions, they are completely 100% obsolete against dynamic models that can evolve and update their weights on the fly. If we actually want to secure this next generation of AI, defenders have to urgently pivot. We need to shift away from rigid payload filters and transition to continuous, real-time, holistic state monitoring frameworks. We're talking implementing robust temporal memory auditing to catch those scattered payloads, deploying real-time perplexity shift anomaly detection to catch those localized weight changes, and utilizing multi-agent alignment systems that actually understand contextual integrity. As we log out of the sandbox today, I want to leave you with this one very provocative question to chew on. If an AI can be tricked into literally overriding its own safety weights during a single conversation, how can we ever guarantee its alignment in an autonomous future? It's a deeply fragile ecosystem out there, and honestly, the challenge for defenders is only just beginning. Keep exploring, keep learning, and I'll catch you in the next explainer.